Hello, my name is Joshua Coady, and I'm an electrical engineering major.
Hi, my name is Gabriel Einstoss. I'm an electrical engineering student.
So let's talk a little bit about the problem. Modern food production brings in huge amounts of carbon dioxide. In urban areas, the lack of land makes it extremely difficult for someone to create a garden or farm when there is suburban or urban areas. I was walking through my neighborhood this week, and I noticed that all the houses have very small land, but they get a lot of sun. Around 11% of the greenhouse emissions from fruits and vegetables is related to the transportation costs. According to the USDA, in 2017, 11,161 megatons of vegetables were imported. So our solution today provides a vertical application for gardening in suburban and urban areas. Now, while this won't be great for the sides of skyscrapers, it definitely can fit into areas where space is limited. So, for example, when I was walking through my neighborhood earlier this week, and those houses that have great sunlight, but they're really difficult to have a garden because you have limited space. So due to the pandemic, we had to split our prototype into two different pieces. Gabriel's been working on the electrical side. We're making sure that the water pump and the power is supplied directly, whereas I've kind of created a little system here that kind of demonstrates the overall system on how it would work from an outside view. What we have here, and I'll have some model overlays as well, is we have simulating the side of a house. Now, don't mind the hard drive, it's here to hold it down, but for the most part, this is just the regular side of the house. Now, on the side of the house, we have kind of our system here. It would allow for the rotation of different beds, and it would keep all of the side of the house, assuming it was in the sunlight, of course, keep all the side of the house ability to garden. Now, another problem that we may consider, especially for us being, active, busy people in the workplace, is that we also have to consider the time commitment, the amount of work that it would take to garden. So it would be different if we had just a regular, garden that was vertical, but that still presents a problem of upkeep. So Gabriel's been working on making sure that we have a really, really good autonomous system so that it can keep track of water, it can keep track of humidity, it can keep track of heat, and it can adjust and change things accordingly. And for my prototype here, I have a stepper motor along with a little controller plugged into my computer. It's running a pretty simple script, but I think that this definitely does show the proof of concept. Across the bed here, we have an assortment of different tools and sensors that go into each of these beds.
For the prototype, we used a Arduino Xiao as our microcontroller with two analog inputs simulating our temperature and soil humidity level. Once these analog inputs pass a certain threshold, indicating the soil is too dry or the temperature is too low on the water, it will trigger either a water pump or to simulate a water heater, we're using an LED. So if we go below that threshold, the water pump will activate, and they work independently, so one function won't affect the other.
Now, a couple things that we really wanted to make sure were important is obviously when you have such a extensive garden, this takes upkeep. This requires energy. So a couple things that we've gone ahead and done. First off, the water consumption, we've really thought hard about this. We think that if the water from the roof, we can get the water to run off into a reservoir, and that reservoir water the plants. Now, while the roof may not be the best example, you could always have some solar panels draining the water into a reservoir, and I think it really does show that you can use the available rainwater to water the plants. Now, a couple other things as well is that while our system is really great here, it's still going to possibly need the assistance of mains power and a water supply. Because while, yes, you may run out of water in the hot days, I think that having it mostly sustainable and then not losing your entire garden because it was hot one day and you ran out of water, I think that is much more sustainable in the long term. We're having to constantly buy new seeds and replant stuff.
So we're going to take a look into the prototype effectiveness. If we use a 10-foot wall as our example, we're able to get 100 square foot of land. If we grow the four most common vegetables consumed in America, which are potatoes, tomatoes, onions, and lettuce, which I know tomatoes are fruit, but given the surveys and the common misconception, it was ranked as the second most consumed vegetable in America. If we only grow one of these four types, we'd be able to grow 100 potatoes, 100 tomato plants, 400 onion plants, and 400 lettuce plants. Now, if we put this into a more realistic case, if we do 40% potatoes, 40% tomatoes, 10% lettuce, and 10% onion, we would have a food yield of around 32 pounds of potatoes, 150 pounds of tomatoes, 20 pounds of onions, and 10 pounds of lettuce. Now, what is this in monetary? How many dollars is this? How much am I saving? Well, the cost of operation is around $80 given the current Raleigh power and water prices, and the price of the yield would be around $350 on vegetables. So you save around $270. Now, this is considering that we only do one yield in a year. The cost of operation for an entire year is 80, and you would be able to do at least two yields in an entire year. So that's $700 on vegetables. Now, what is the impact of this solution? Well, on an individual case, it would be around $700 of food a year. That's around 52 pounds of CO2 emissions being cut. Now, this is only CO2 emissions due to transportation, which accounts for 11% of CO2 emissions on food production. Now, it might not sound like a lot, 52 pounds, but if we take this to a national scale and we say that 1.5 of the single family houses in the United States have one of these, then it would cut down around $14 billion of food cost and 5,000 tons of CO2 emissions. Now, how feasible is this? Well, for an individual standpoint, the cost of implementation is around $2,000 of materials and installation, and we're looking around $350 to $650 on topsoil, depending on what type of topsoil you use, but this is for 100 square feet. So what is the return on investment? With an annual yield of $700, you would be able to pay off the investment in 3.5 years, and if we do a 10-year service life without requiring any maintenance, it would be around $4,500 that you save on groceries after paying off your investment.